For all of calculus, we've been concerned with answering questions surrounding dynamics on the Cartesian plane. And we have one more question that we want to find the answer to, and that is, if we have a curve, let's say a curve like that, and we were to select a point, like let's say this is point A and another point B on the x-axis, and we wanted to find the area under the curve between points A and B. So we're talking about this area right here. How do we find area on a Cartesian plane? So let's say that we in particular have this curve. Let's say it's a curve of x squared. I'm going to take some points. We're going to have 1, 2, and 3. And what we want to do is to find the area underneath the curve between 0 and 3. What the cavemen would have done a long time ago when they want to find the area underneath the curve would have been to just say, okay, let me draw a big rectangle. And this rectangle is just going to tell me the area underneath the curve. But you can see that it's kind of an overestimation because it doesn't give me only the area underneath the curve, but it also comes up here. But what would be the area underneath the curve if we use this method? This would be the 3 units here times the 9 units here, because 3 would go up to 9 here. So the area of the section under the curve here by this method would be what? 27 units squared. So let's see if we can come up with a more accurate way of finding the area. So here we have our x squared curve again. And instead of drawing a big rectangle from here to here, what we're going to do is that we're going to actually draw some smaller rectangles. So at every unit on the x-axis, we're going to draw a rectangle there. So we're going to say from 1, let's label these, each of these get their own rectangle, going all the way over here, right? But you can notice that this is still a bit of an overestimation because we still have this extra bit up here, we still have this extra bit up here, and we still have this extra bit here. So what would be the area here? Well, the base for each of them would be 1. This would be 1 unit, 1 unit, 1 unit. And the height of the rectangle would be 1 squared, which is 1, 2 squared, which is 4, and 3 squared, which is 9. So that would be 1, which is the base, times 1 plus 4 plus 9, which would be equal to 14 units squared. So notice that first our estimation was 27 units, now it's 14, but this 14 is still an overestimation. So how are we going to correct this? Let's see if we can make even smaller rectangles to get a more accurate estimation of the area under this curve. So what we're going to do now is, instead of making the base of each rectangle an entire unit, we're going to make it half unit. So one rectangle will stop there, here, and here. So we'll have one rectangle coming here, another one starting here, then here, then here, and so on. Now again, notice that this is still a bit of an overestimation. But looking at this, the base will always be half times the height. Let's square each of these units. 0.25 plus 1 plus 2.25 plus 4 plus 6.25 plus 9. And all of this sums to give us what? 11.375 units squared. So all in all, while our rectangles are giving us some overestimations, what this is telling us is the smaller I get the base of my rectangles to be, the more accurate the area is. So if I want to find the area under the graph between 2 points, all I need to do is to make the rectangle's base as small as possible in order to get an area as accurate as possible. Let's put it this way. We're saying, in general, that we have a curve and we want to find the area between points A and B underneath the curve. So what we're going to do? We are going to be summing the area of each rectangle. So here the base of each rectangle would be given by the distance from A to B and dividing it in n rectangles. And then the height would be f of x. And the product of those two will be the area of each rectangle. So summing that from I equal 0 to n, we will have the entire area under the curve. But as we said before, for us to have an area as accurate as possible, we need to have the base of the rectangles be as small as possible. For the base of the rectangles to be as small as possible, we need as many rectangles as possible. So what are we going to do? We are going to say, alright, we are going to let n approach infinity. So how are we going to do that? We're going to say, we're going to be finding the limit of, let's take out the b minus a all over n, since that would be a constant. We're going to be finding the limit of f, the sum of f of xi from I equals 0 to n as what? As n approaches infinity. So what is this saying to us? This is saying to us that we are no longer cavemen who draw rectangles to find the area underneath curves. What this is saying is that in order for us to find the area underneath the curve, and I must say very much accurately, all we do is find the limit of this expression as n approaches infinity. By letting n approach infinity, we could say that we're drawing rectangles whose widths are so small that they could be described as being infinitesimally small. So we're not going to bother with the caveman behavior of drawing these rectangles and adding their area together. No, that's caveman style. As intelligent cave students, what do? We find the limit of this expression as n approaches infinity. Let's look on this example. Let's find the area under the curve x squared between 0 and 3. So, as I said, it's the limit of b minus a all over n times the sum of f of xi from I equal 0 to n as n approaches infinity. So let's do this. We have the limit as n approaches infinity of b minus a. What is b? b is 3 minus a being 0 all over n. So what this is saying to us is that each rectangle has a base of 3 over n units. And so the corresponding f of xi value that we'll be summing will be 3 over n. That will be the first one, but remember, I know it's x squared, so this will be the first x value and this will be squared. What will be the second x value? Since each unit is 3 over n, then the other one would be 2 times 3 over n, which would end up be 6 over n and squared. Then we have what? What's 3 times 3 over n? That would be 9 over n squared. And this will be the pattern of the sum as we go all the way up to what? 3. Because we'll be summing from 0 to 3. So instead of writing it just 3 like that, we're going to put it in the same fashion, which will be 3n over n all squared. So this now simplifies to the limit of 3 over n times the sum of 3r over n all squared from r equal 1 to n as n approaches infinity. So let's go to the other page now and simplify this. So we have what? We want to look at it, we want to have it looking as clean as possible. So we just have 27 over n cubed times the sum of r squared from r equal 1 to n as n approaches infinity. Now, hopefully you remember when you were doing mathematical induction, and you would have learned that you're supposed to be able to prove that this summation was equal to something, and that would be the limit of 27 over n cubed. So what would this be equal to? This would be n times n plus 1 times 2n plus 1 all over 6 as n approaches infinity. So if you want to, for the fun of it, you can always go and confirm by mathematical induction that the sum of r squared from r equal 1 to n would be equal to this. So upon simplifying a bit further, we get to see that this is 9 over 2 times the limit of 2n squared plus 3n plus 1 all over n squared as n approaches infinity. And the answer will actually be 9. So in other words, what this is telling us is that the area underneath the curve x squared between 0 and 3 would be 9 units. It's squared, and that's the exact area under the curve x squared between 0 and 3. Instead of doing that long process of finding the limit of b minus a all over n times the sum from I equal 1 to n of f of xi as n approach infinity, what we do is that we just integrate f of x with respect to x from a to b to find the area underneath the curve between a and b. So how exactly we carry out this much shorter process of integration, we will see in the next video.